Welcome back, everyone, to MAT1841. We're back in our usual room. Hopefully, everyone can hear me all right, and there's no more problems with the tech setup. So, what did we do last time? So, last time, let me just write this down. Last time, we introduced air-to-Trinity random graphs, and we introduced the concept of phase transitions. Graphs and phase transitions. And we also ended with a discussion of some of the common techniques. So we talked about the first moment method and the second moment method, which are basically correspond to Markov and Chebyshev inequalities for proving phase transitions in graphs, basically taking advantage of the fact that for many phenomenon, if there's a discrete count of something, you can't have between 0 and 1. And so therefore, if you can bound something away from 1, or you're bounding something away from 0. Now, I think we ended last time with the second moment method, and I think, let's see, did I discuss the corollary of it? So actually, let me go ahead and write this corollary in on these sets of notes, since it's a corollary of the second moment method, basically just formalizing the proof we used for the triangles. So a corollary of the second moment method. So remember, the second moment method is just that if you have a random variable that is with expectation of x is greater than 0, then if the variance is little o of the expectation squared, then x is greater than 0 almost surely. So basically, if the variance is much smaller than the expectation squared, well then with high likelihood, you're not going to hit 0. And the corollary, sorry, my chart is not tall enough there. Okay, so a corollary of that is that if we let x be a random variable with the same setup, with with expectation greater than 0, if we know that the expectation of x squared is less than or equal to the expectation of x squared times 1 plus the o of 1, when x is greater than 0 almost surely, as n approaches infinity. So of course, everything we're doing in this section is in the limit of large n. Okay, and note that one of the difficulties we had with using things like the second moment method when we were proving stuff about triangles is, well, you don't have independence. And so computing variance is harder. And so like when we were doing the proof of the triangles, what we had to do is we had to split up like all different 3 cases of like what could happen with like 3 triangles, because each of our edges was generated independently, but the triangles weren't generated independently. And so we had to do that sort of classification in order to prove something about a bound on variance. Okay. Any questions about what we went over last time? So today we're going to apply all these techniques. And so we're going to review all that and talk about diameter and isolated vertices. So recall we had this nice handy table of some common phase transitions in air-to-Trinity random graphs. So basically, as you increase the probability of edges, the graph like changes qualitatively in behavior. At first, you only have a bunch of random like trees that aren't connected. Then you start having some cycles. Then you have much bigger components. Then you have a giant component, and so on. One of the phase transitions we're going to be talking about today are things like diameter. So at this particular probability of having an edge, the diameter suddenly becomes 2 almost surely. So once you get past this, the diameter becomes very small. And with high likelihood, every node in the graph is no more than distance 2 away from every other node. So that's what we're going to get started with. And we're also going to talk about the disappearance of isolated vertices. So today, diameter and isolated vertex phase transitions. Okay, so let's start with a theorem. And this is just going to be the diameter phase transition. So the property that an air-to-Trinity random graph G of np with n vertices and probability p of each edge independently drawn, the probability that the property that this has diameter 2 has a sharp transition at p is equal to root n times square root of log n divided by n. And recall that for the purposes of the random graph stuff, we're always going to be working with the natural log rather than base 2 log. And so let's try proving this. So let me remind you guys for the sharp. Actually, can anyone tell me what a sharp transition is? I just want to make sure everyone's still on the same page.
So if for P is anything that's less than that, you don't have the property that's greater than equal to that.
Yes, but what does it mean for it to be sharp? So remember, we talked about two different kinds of phase transitions. So one was the sort of asymptotic phase transition, and one was this sharp phase transition. So those had slightly different characteristics based on as your function gets smaller or as your function gets bigger asymptotically. So for a sharp transition, what you have is you have some constant, but as you vary the constant between above and below some real value, you get the transition. Whereas with the non-sharp ones, it might be a slightly smoother transition. Is that all right with everyone? Okay, so what do we mean precisely by a sharp transition here? So if P is equal to C times the square root of ln n over n, for C greater than root 2, diameter is greater than 2 almost surely. For C less than root 2, diameter is less than or equal to 2 almost surely. Okay, so that's the property that we care about. And the important thing is we have some constant here. So we don't need to be asymptotically different than root 2 times the square root of ln n over n. You just have to be slightly different in terms of that constant C. So let's prove this. So what is the general proof strategy? So how did we prove stuff about triangles? Well, when we were trying to prove stuff about triangles, what we cared about is just counting the number of triangles. And we defined some random variable as just the number of triangles, and we're like, well, does a triangle exist? Can we do something similar for diameter 2? Can we count something and say that, well, if these things exist, then your diameter isn't 2. And if these things exist, then your diameter is 2.
Is diameter like the length, the longest?
Yeah, the diameter is the longest distance between any two nodes. So this is in some sense a combinatorics question. Like, what are we trying to count? Well, as you just said a moment ago, the diameter is the length of the longest path. And so one thing you might consider counting is the number of pairs of nodes that are greater than distance 2. And so if that distance is, if that number is 0, well, then that means the diameter is less than or equal to 2. If that number is anything other than 0, then, well, your diameter is greater than 2. And so once we recast it in that form, we can use all the same techniques that we use to prove stuff about the existence of triangles in graphs. But instead, this time we're going to be talking about the existence of these bad pairs, basically. So let's formalize that intuition a little bit more. So if the diameter is greater than 2, then there must exist non-adjacent vertices I and j, such that no other vertex is adjacent to both I and j. Right? Because if they're adjacent, then the distance between them is 1. If they're and so they clearly can't be adjacent. And we also can't have any intermediate node that you can use to hop between the two in 2 steps total. So we're going to call such a pair bad. And all we're going to do is, well, we just need to count the number of bad pairs. And so we're going to use our usual strategy of just defining some indicator variable on whether or not a particular pair is bad. So let the indicator I sub ij be equal to 1 if and only if pair ij is bad. And then we're going to let x be equal to the sum for all I less than j of I sub ij. And this is just the number of bad vertices. And well, now we just need to use the first and second moment methods and do the same analysis that we did with the triangles. So what's the expected number of bad vertices? Well, the expected number of bad vertices, well, you have n choose 2 because that's the number of pairs. So number of pairs such that I is less than j. I mean, just the number of pairs total. And what do you need? You need you need a factor of 1 minus p because you have some probability that there does not exist ij, so non-adjacent. Because with probability p there is an edge, so probably 1 minus p there isn't an edge. And additionally, we have probability 1 minus p squared to the n minus 2. And this term, this part of this comes from the probability a vertex is not adjacent to both I and j. And this here is just the number of other vertices. Okay. So then basically what we have is we have some I, and we're asking some other vertex b. So you have some probability p. So if it's adjacent to both of these, that would be p squared, right? And it has 1 minus p squared probability of not being adjacent to both of them. And of course, we also have this other term p here. So we want that to also be a 1 minus p. So this is why we have the 1 minus p, as well as 1 minus p squared to the n minus 2. And this gives us the expected number of bad vertices. And well, let's see what happens for a particular value of p. So let's set p be equal to c times root ln n over n. So then the expectation of x is approximately equal. So like we did last time, we're going to be playing really fast and loose with our constants here because we're only caring about asymptotics in this section. So this is approximately equal to n squared over 2 because n choose 2 is about n squared over 2. Not quite, but close enough. Times 1 minus c times root ln n over n times 1 minus c squared times ln over n to the nth power. Now, of course, this should be n minus 2, but again, we're playing fast and loose with constants. So this is approximately equal to n squared over 2 times the x e to the minus c squared ln n, which is approximately 1/2 n to the 2 minus c squared. Okay, so like I said, we're playing really fast and loose with approximations, but since we only care about asymptotics, this roughly speaking works out. Is everyone all right with that? I have just suddenly done a ton of approximations all at once. Okay, but now we can say what happens for c greater than root 2. Well, the limit as n goes to infinity of the expectation of x is equal to 0, right? Because it keeps on getting smaller. So in the expectation, you don't have any bad pairs when c is greater than root 2 for large n. So by first moment method, g of np almost surely has no bad pair. And hence diameter 2. Okay, so basically, if you don't have any bad pairs, you can't have diameter 3 or higher. So this is the easy direction, because this is the direction where we're just using the first moment method. The other direction is the hard direction, which is to show that when it's less than root 2, well, then you almost surely do have a bad pair. And so now, well, let's consider that case. So consider c less than root 2, where we have the limit as n goes to infinity of the expectation of x is equal to infinity, right? So we know this because we were just plugging that in. But unfortunately, just knowing the expectation is not enough to use the second moment method. You need, well, the second moment of the random variable x. So we will use second moment method. In order to do that, we have to actually compute the second moment. So what's the expectation of x squared? Well, that's just equal to the expectation of the sum over for I less than j of I sub ij squared. Let's make sure to put that in the correct brackets. So this is equal to the expectation of the sum over I less than j of iij times the sum over, let's do k less than L of ikl. Which is equal to the expectation, or we can combine both of the sums together. So I less than j and k less than L of iij and ikl, which is equal to the sum over I less than j, k less than L of the expectation of iij and ikl. But now we're stuck, right? Because, well, unfortunately, these things aren't independent. The fact that two things are like, if one thing's a bad pair, that affects whether or not something else might be a bad pair. And so we unfortunately have to divide this up into a number of different cases, like we did with the triangles. Luckily, the cases here are a little bit easier than the cases for the triangles, but we still do end up with 3 different cases. So we're going to use the same method to divide them up. So this thing is equal to the sum over I less than j, k less than L of the where all of them are distinct. All I, j, k, L are distinct. Okay, so this is one of the easy cases. So I, j, I, k, L, they're all distinct, and so you have independence, and you can split up your expectation. Plus, well, that's the case when they're all distinct. What are some of the other cases? So one case is you have all 4 distinct. What are some of the other cases? Yeah, exactly. So let's say that they're not all distinct. You only have 3 total things. So let's say the set I, j, k, I less than j, and all I, j, and k distinct. And we have the expectation of I, ij, and I, ik. Okay, so one of the nodes is shared between the two. You have the case where, well, both of them are shared. So the expectation over just I less than j of the expectation of I, ij squared. So we're doing the exact same thing. We're splitting it up. And we notice that these are easy to upper bound. This one is hard. So when all 4 vertices are distinct, then that means that there must be 2 bad pairs, ij and kl, for iij, ikl to be equal to 1. Okay, so you need them both to be bad in order for that to contribute anything to your sum. And so that's the only case we're going to worry about. Well, then that means that for all u not in I, j, k, L, at least one of IU and JU is absent, and at least one of your KU and LU is absent. Okay, because both of them have to be bad pairs. Well, what's the probability of both absences? The probability of both absences anyone? So remember, we computed the probability of an absence, right? So just 1 minus p squared. And so for a particular u, the probability of both absent, the probability of both absences is in 1 minus p squared squared. Because these are distinct, so we can just do that. And so therefore, you know, the expectation of Ij, ikl is less than or equal to 1 minus p squared times 2 to the n minus 4. Because we have n minus 4 possibilities for the choice of u. And so this entire thing is less than or equal to 1 minus c squared ln n over n to the 2n times something that's 1 plus the low o of 1, which is less than or equal to n to the minus 2c squared times 1 plus something that's the low o of 1, which then implies that the summation over I, j, k, l, I less than j, k less than l, all distinct, of this expectation is less than or equal to 1/4 n to the 4 minus 2c squared times 1 plus the low o of 1. Does anyone know why we have the 1/4 there? Or did I go through these approximations too fast? So the reason for the 1/4 is because 1/4 less than 1/4 of the n to the 4th 4 tuples have I less than j and j less than and k less than l. Right, because basically what we're doing is we're looking at all the cases where I is less than j and k is less than l, and each of those, roughly speaking, takes out half of your possible things. And so you end up with 1/4 n to the 4 minus 2c squared times 1 plus the low o of 1 for the basically as an approximation factor. So you guys should tell me if I'm either boring you with this or I'm going too fast, since I'm not actually sure which right now.
I think it's going fine.
Okay, I'll keep on going then, but please do let me know if that's the case. Well, now we need to carefully analyze the next case, which is when there's only 3 distinct vertices. Well, if there are only 3 distinct vertices, if Ij, Ik is equal to 1, well then you know that for all u not in the set Ijk, either there is no edge Iu, or there is an edge Iu, and both Ju and Ku are absent. Okay, because of course I is shared between the 2 pairs, and so we like either that pair, like that one fails, and if that fails, then well, you don't have to worry about the rest. Or if that one doesn't, that event doesn't happen, then you need both of the other 2 cases to happen. So what is that probability? The probability is, well, 1 minus p for the probability there's no edge Iu, plus p for the probability that there is one, times 1 minus p squared, which is unequal to 1 minus 2p squared plus p cubed, which is approximately equal to 1 minus 2p squared for a single u. And yes, we are just completely throwing out the cubic term. So thus, what we know is that the expectation of Iij, Ik, sorry, not KL, Ik is approximately equal to 1 minus 2p squared to the n minus 3, which is approximately equal to the exponential of minus 2p squared times n minus 3, which is approximately equal to the e to the minus 2c squared ln n, which is approximately equal to n to the minus 2c. So plugging in the values of C that we have there. So together, this implies that our expectation over triples I, J, K for I less than J of the of the sum. I meant for that to be the sum, not the expectation over that, the sum over that of the expectation of Ij, Iik is less than or equal to n cubed times n to the minus 2c squared, which is equal to n to the 3 minus 2c squared. So now we're almost done because the third case is easy. So when only two distinct vertices, well then the sum over Ij of the expectation of Iij squared is equal to the expectation of x, which is approximately equal to 1 over 2 n to the 2 minus c squared. So putting that all together, we have the expectation of x squared is less than or equal to 1/4 times n to the 4 minus 2c squared plus n to the 3 minus 2c squared plus 1/2 n to the 2 minus c squared, which when we collect the other terms is equal to 1/4 n to the 4 minus 2c squared times 1 plus 4 to the n to the minus 1 plus 2n c squared minus 2. And if c is less than root 2, then we know that the expectation of x squared is less than or equal to the expectation of x squared times 1 plus the O of 1. Okay, so that entire computation was just to give us this bound on the second moment. And once we have this bound on the second moment, well, by a second moment argument, which is basically just going through Chebyshev, except we're not explicitly writing out Chebyshev. So by a second moment argument, the graph almost surely has at least one bad pair. So the diameter is greater than 2. All right. Okay, any questions on all that? So let's go ahead and see another example. So I think, how am I doing on time? Oh, I still have another 20 minutes. Okay, let's see another example that uses the same argumentation style. And then when we're talking about component sizes later, which we might get to today, but we might not, we'll have to use a much more complicated argument style. I'm just showing you a couple of examples of applying this basic first and second moment argument to prove a phase transition. Whereas later we'll see some more complicated arguments for some of the other phase transitions. So what were the other things we said? We wanted to talk about isolated vertices. So this one was on this end of the spectrum. So for high probability of edges, you have a very low diameter. One of the other things we care about is a little bit further up. You might care about the disappearance of edges. So, disappearance of isolated vertices. So at some point, it becomes unlikely to have any vertices that are on their own. And it turns out this is a fairly easy argument to make because, well, all you're doing is counting up the number of isolated vertices, right? And so we can make use of all our same techniques, just count the number of isolated vertices, and then that gives us where that phase transition happens. So, which brings us to our theorem, which is that the disappearance of isolated vertices in G of NP, so the area on your graph, this also has a sharp transition threshold of ln n over n. Okay, so above this, you're unlikely to have any isolated vertices, and below this, you're very likely to have isolated vertices. And let's prove it. So as I said, this is relatively straightforward application of the techniques we've been studying. So it's going to let x be equal to the number of isolated vertices. So what's the expected number of isolated vertices as a function of n and p? What's the probability that a single vertex is isolated?
1 minus p.
Yeah, 1 minus p to the n, or n minus 1. But yeah. And so that gives us immediately the expectation of the total number of isolated vertices, right? So len, the expectation of x is equal to n times 1 minus p to the n minus 1. Because, well, each one has linearity of expectation holds even when you don't have independence. And so that's relatively easy. Well, now we can just say, well, let's let p be our transitional value. So let p be equal to c times ln n over n. Well, len the limit as n goes to infinity of the expectation of x is equal to the limit as n goes to infinity of n minus c ln n over n to the n, which is equal to the limit as n goes to infinity of n e to the minus c ln n, which is equal to the limit as n goes to infinity of n to the 1 minus c. So if we have c greater than 1, then the expectation of x goes to 0. So by a first moment argument, almost all graphs have isolated vertices. Okay, so well, that's the easy side, right? But what happens if c is less than 1? If c is less than 1, well, then the expectation of x goes to infinity. So again, we need a second moment argument. Because we just need to show that you're not going to deviate so far away from your expectation that you're going to have isolated vertices. When c is greater the yes, I do believe so. Wait, so no, when c is greater, wait, did I get this backwards? Goes to 0. I think I'm missing a no. Oh no, yeah, I'm missing a nowhere. Have no isolated vertices. Yep, yeah. Yeah, because if it goes to 0, if there's an expectation you don't have any isolated vertices, then with high likelihood you don't have any as well. Yeah, so that's basically the intuition behind this, which is that if your probabilities of having, basically, if you think about it, if your probability of having of a single edge was 1 over n, then the expectation you have degree 1, right? And so if you in the expectation you have degree 1, then that means some things have less than degree 1. Basically, and so that clearly isn't good enough. And so the question is, at what level do you have in expectation a high enough degree that that you don't have any edges, that don't have any vertices that are isolated? But yeah, and so as that probability goes up, well, it's very unlikely to have things that are degree 1. Okay, but for c less than 1, well, then we need the second moment argument. So let's start by assuming that c is less than 1. And we're going to let x be equal to the sum over all I of I sub I. That's actually a really terrible name, I sub I, but it's the indicator variable for each vertex being isolated, where indicator I sub I is equal to 1 if I is isolated. Is isolated. There are lots of I's and is's in the statement. Is isolated, not is elated. 0 else. Well, then we need to compute the second moment. So what's the expectation of x squared? Now, of course, you don't have independence, because if one vertex is isolated, that does affect whether or not another vertex is isolated, right? Because when one vertex is isolated, you know something about the other vertex, which is that it doesn't have a connection to the first vertex. So when we're doing the computing this, we do the same thing, but we divide this up into 2 cases. So we have from 1 to n of the expectation of I sub I squared. So that's when basically we have the usual double sum and then we break it apart. I'm not going to go through all the steps of that, same as before. That plus 2 times the sum over I less than j of the expectation of I sub j. Right, so we had that double sum and then we broke it up and we took out all the ones where they're equal because that's the easy case. And then we had all the cases where they're not equal. And this is, of course, the isolation is not independent. And so we can't actually multiply these probabilities through. But luckily, it turns out we can compute that fairly readily. And it turns out we don't even have to break it into as many cases as we did in the last case, because vertices being isolated, there's fewer cases to consider. So, well, this first term is just expectation of x, because that's just the indicator variable. Indicator variables squared are just the indicator variables themselves. So the first term is just expectation of x. The second term is n times n minus 1, because those are all different choices of pairs, right? Times the expectation of I1, I2 for any one particular set I1, I2. And so this is equal to the expectation of x plus n times n minus 1 times 1 minus p to the n minus 1. So that's the probability that I1 is isolated. But what's the probability that I2 is isolated? 1 minus p to the n minus 2, right? Because you already know that the edge between 1 and 2 doesn't exist, condition on that. And so this actually gives you the full computation for these two expectations multiplied by each other. And so we're basically almost done. So this is just the expectation of x plus n times 1 minus p to the 2 times n minus 1 minus 1. Oh, come on. And thus, we know that the expectation of x squared divided by the expectation of x squared is equal to n times 1 minus p to the n minus 1 plus n times n minus 1 times 1 minus p to the 2 times n minus 1 minus 1. I'm just plugging everything in here now. Hopefully I don't have a typo as I copy this over. And you just, oh, did I make a mistake there?
Where's the factor of n minus 1 going? Seems like you just dropped it.
Wait, sorry, where?
From the middle line to the last line. The last line of the second.
Oh, oops. Yes, it's still there. Like I said, I'm just copying things over now because this is all just straightforward computation. I'm not doing anything tricky here. So just a lot of algebra. Okay, but we can simplify this out. And what you'll notice is that for p is equal to c ln n over n with c less than 1, well, the limit as n goes to infinity of expectation of x equal to infinity, and we know that the limit as n goes to infinity of the expectation of x squared divided by the expectation of x squared, that's equal to this limit as n goes to infinity of 1 over n to the 1 minus c plus 1 minus 1 over n times 1 over 1 minus c ln n over n. This theorem goes to 0. And so this is just equal to the limit as n goes to infinity of the remaining term, 1 over 1 minus c ln n over n. Of course, the 1 minus 1 over n also just goes to 1. And this turns out to be equal to 1 plus the O of 1. And therefore, we can just apply a second moment argument. So by a second moment argument, almost all graphs have isolated vertices for c is less than 1. Okay, so we've now seen several examples. These are straightforward applications of these moment methods. They allow you to prove structural properties of graphs without have that change as you cross some phase transition as a parameter varies. Now, we've been doing this in the very simple model of an arbitrary random graph where we let n be super big and we only have a single parameter. You can envision doing these sorts of analyses with other parameters as well, or with other random graph models. which we're going to do a little bit of in a couple of days when we work on percolation theory. So there'll be a different random graph model that has some application to real world material science. But I have another 10 minutes, so I'm going to go ahead and, if there aren't any questions, I'm going to go ahead and try to start explaining some of the proof for how to do these phase transitions for component sizes, because they get a lot more finicky. So actually, let me move this into lecture 16, since we're a little bit ahead. So this is going to be component sizes. And so what we're going to do is we're going to start off by, well, defining a new way of thinking about the graph. So right now, the way we're thinking about a graph is, well, you scatter a bunch of nodes onto some Platonic space, and then you ask if any pair of nodes are connected, right? And then once you do that, you've generated an entire graph. Now, it is entirely equivalent, though, if you have some sort of dynamic process exploring the graph to only generate edges on command. So basically, you don't have to generate the entire graph at once. You can think of it as equivalent to, as you have some walker exploring the graph to generate the edges, and then save the edges after you've generated them, but to decide only when you're about to go to a new node whether or not it has an edge to it. And that's going to form the idea of an idea that we're going to make use of in proving stuff about component sizes, which is we're going to have some process that's exploring the graph and only generating the graph as we explore it. This is going to be useful in talking about component sizes. Component sizes for G of n. And we're going to do D over n for D greater than 1. Okay. And all I'm going to do today is just describe the process, and then we'll actually do the proof next week. Today, Friday? No, today's not Friday. Today is Thursday. Yes, today's Thursday. Sorry. Yeah. So let's consider a breadth first search. So some of you may have taken algorithms, and so you'll be familiar with this, but fear not, we will describe what this is. So this is a BFS on a graph. So the way this works is we're going to explore all neighbors of a starting node. And then we're going to explore all neighbors of the neighbors. And so on recursively. Okay, so basically what we're going to be doing is at some point, we're going to have some small core that we've explored. And then we're going to look at one step further. So like all the neighbors of these things. And so that's going to extend out. And so we're going to have some frontier. So we're going to take another step out. We're going to have some frontier. And this is all going to be there to explore some big connected region, connected component. Right? Because as you're exploring outward, eventually you'll hit the boundaries of your connected component, and then your process will stop. And so somehow we'll be using this process to measure the sizes of the connected components, because we have some dynamic process that has some termination criteria. And then when that terminates, that tells us that we've explored an entire connected component. Let's define these things a bit more explicitly. So what is the frontier? So we're going to say that this is discovered but unexplored vertices. Discovered but unexplored vertices. And what does discovered means? Discovered means neighbors of vertices that we've explored. So when you go to a node, you can look around and be like, what nodes can I walk to? But you don't have to walk to that node yet. And so that's what it means to be on the frontier, is these are the things that you see in the distance, but your process hasn't walked there yet. And notice that when the frontier, size of the frontier, is equal to 0, well, what's happened? That means we're done. We're done exploring an entire connected component. And importantly, we can imagine generating edges only when we need them. And this makes the process easier to analyze, right? Because instead of having to generate all these edges first, and you have and then asking, well, does this particular edge exist? Instead, when you're on a node and you're exploring that node, you're basically looking around and seeing where you can walk to. When you're doing that process, you don't have to look backwards at the places you've already been because that's already explored. So you're basically looking at every one of the remaining nodes in your universe of nodes. So in your entire graph, and you're asking, do I connect to you? Do I connect to you? Do I connect to you? And on each of those, you have a p probability of connecting to it. And so basically, you're generating the graph as you come to it. And this is entirely equivalent to generating it all in the first place. And now what we're going to do is we're going to define a step. A step as the full exploration of a single node. So allow this to say finding all its neighbors. Finding all its neighbors, but not walking to them. And so this means that we've now connected together our search process with the size of a connected component, right? Because the number of steps you've taken is the size of your connected component that you have explored. And whenever you explore a node, you move it from the frontier over into the set of explored. And so at the end of the day, your process terminates when you have successfully explored an entire connected component. And you can measure this instead in terms of the length of your search process. And I think that is a natural place to stop. When we come back tomorrow, I will describe a slight modification of this process that'll give us something that's easier to compute with. And then they'll give us an upper bound on the sizes of these components. And then that'll tell us something about the overall sizes of components in our error-differential random graph. Yeah, any questions here on chat? Okay, class dismissed. We will be back here tomorrow, not over in Bayonne. So we will be back in Bayonne on Wednesday. So, and reminder, your homework is, I think, due tomorrow evening, I think is what I said. So, oh, and I have looked at all of your proposals. They all seem reasonable. I will spend a little bit more time and give like more detailed feedback. But for now, you can just, all of the proposals are reasonable ones. So, okay, bye everyone.